So this chart we've seen, I've drawn before on the chalkboard, is the abundance in a sense, uh, as well as the mass per particle versus the atomic mass. And if you're falling down the y-axis, you're gaining energy, right? So uranium fissions and gains energy, hydrogen fuses and gains energy, and each time we ignite a new material in the star, there's less energy to gain. And eventually we get down to iron and it's at the low point. There's no way to gain energy out of iron. Of course, there'll be some attempts at iron fusing in the core, and that's going to suck energy out. It says that the star contracts and it heats up, that iron will essentially draw energy out. Right? And so here is the abundances. And this is kind of what we expect is hydrogen and helium are pretty abundant. And then next is carbon. And that makes sense because helium makes carbon, and then carbon and helium make oxygen. And what you're seeing is that the most abundant things, the peaks on this graph, are things you can make from helium and other peaks on the graph. And the things in between, like lithium and beryllium and boron, those are things you can't make, not easily. And the stuff in the low points in this graph. Right? So some of the stuff that we see is going to be formed in the shell fusion process, the onion that makes up these stars. The rest of this has to form in that final collapse when the iron core collapses and it can't fuse into anything else. So this is the death of high mass stars. This is what supernovas are. Right? This core builds up, and the mass of the core is going to increase, but the degeneracy pressure is basically fixed. And so the density builds up, it keeps trying to contract. Eventually, that contraction takes place. Eventually, gravity wins. It contracts, and the electrons that are initially holding up the iron core, they are moving so very fast. They're bouncing around the core at high speeds. They're not very well contained. It becomes likely what will happen is, rather than be forced together, a proton and electron will merge and they'll form a neutron and a neutrino. Right? The neutrino forms because you have to have some remnant of the electron around. You have to conserve the number of leptons. And oops, go back. And the proton goes to a neutron because you conserve the number of quarks. And so this process basically uses up all the protons, all the electrons, just forms neutrons and neutrinos. And the neutrinos don't stick around. They leave immediately. And so that means it's irreversible. You're left with a ball of neutrons that can't make anything else. All right. And so this remnant's going to be what we'll eventually call a neutron star. Now, the outer layers of the star are going to contract. And once that neutron star forms, the neutrons support it with degeneracy pressure, which is significantly stronger. And that uh, is basically going to be a collision between the outer layers and the core, and it's going to bounce. It's going to throw everything outwards, and all the other elements that are made are going to essentially form in that collision, in that bounce inwards and outwards. Is that you're going to essentially get this burst of energy that allows all these unprofitable fusions to occur, and it's going to form everything else. And that energy release is going to push everything outwards into space, and you're going to have remnants left over with everything else in it. And here is a famous supernova. It's in Chinese records from 1054 of a star that was new, visible during the day for a month. You could read by it at night like a full moon. And there's been a few others like that we'll talk about.